Quantum computers aren't just a souped-up version of the laptop on your desk. They're a completely different species of machine. They play by the strange, mind-bending rules of quantum mechanics, and that, right there, presents a massive challenge.
So how do you give instructions to a computer when its most basic parts can be both a 1 and a 0 at the exact same time? How do you write a program for a reality that seems to be built on probability? That's the big question we're going to dive into.
Okay, to really get to the heart of this, we first have to understand the fundamental night-and-day difference in how classical and quantum computers even store information. It all comes down to their most basic building blocks. And the difference here? Well, it's everything. A classical bit, that's just a light switch. It's either off, a 0, or it's on, a 1. Simple. But a qubit? A qubit is more like a globe. It can be at the North Pole, that's a 0, or the South Pole, that's a 1. Or, and this is the key, it can be any point on the surface in between. This state of existing in all those possibilities at once is called superposition, and that globe of possibilities, that is what physicists call a Bloch sphere.
So you can see why our old programming tricks just won't cut it here. To control this whole universe of possibilities, we can't use the simple on or off language of classical computers. We need something totally new. We need a way to speak, well, quantum.
And that is where our main tool for this new world comes in, Qiskit. The easiest way to think about it is like the Python of quantum. It's an accessible, really powerful toolkit that lets us start writing algorithms for these incredible new machines. Okay, so formally, Qiskit is an open-source SDK. But what that really means is that it's the bridge, it's the translator between the code we type on our laptops and the truly mind-bending physics that's happening inside an actual quantum processor. It turns our ideas into real operations that manipulate qubits.
At its heart, a Qiskit program really just has three main pieces. First, you've got the quantum register. Think of that as just the container that holds our precious qubits. Second is the quantum circuit. And that's the recipe, right? The step-by-step instructions for what to do with those qubits. And finally, the Arrow simulator. This is super cool. It's like a perfect virtual quantum computer that lets us test our recipe before we send it to the real expensive hardware.
All right, so we have our recipe, the quantum circuit. But what are the words? What's the language it's written in? Well, the grammar of quantum programming is built on these fundamental operations we call quantum gates.
So a quantum gate is basically a single operation. It's the verb in our quantum sentence. Just like classical computers use things like and not gates, quantum computers use their own gates to manipulate the state of a qubit. It's all about performing a very specific rotation on that Bloch sphere we saw earlier. Now, let's talk about the rock stars of the gate world. First up, the Hadamard gate, or H-gate for short. This thing is like a magic wand. It's what unlocks the real power of a qubit. It takes a qubit that's sitting there as a solid 0 or a 1 and instantly puts it into a perfect 50-50 superposition of both states at once. This is the starting line for so many quantum algorithms. And the other superstar? The C-naught gate, or controlled knot. This gate takes two qubits and links them in a way that Einstein famously called spooky action at a distance. It creates entanglement. Now the state of one qubit instantly affects the other, no matter how far apart they are. Their fates are literally intertwined. So now we have these two incredibly powerful tools in our belt, superposition and entanglement. And by combining these gates in clever ways, we can start to build quantum algorithms that are capable of solving problems that are just impossible for any classical computer to handle. A fantastic example of this is an algorithm called Grover's search. Imagine you're looking for one specific name in a massive, totally unsorted phone book. Classically, you just have to slog through it, right? On average, you'd check about half the names. Grover's algorithm, though, can find it dramatically faster, a huge speed up for this kind of messy search problem.
So how on earth does it work? Well, the algorithm starts by using those Hadamard gates to put the system into an equal superposition of every single possible answer. At this point, every potential solution has the same tiny probability. Our target is basically lost in a sea of possibilities.
Okay, but here's where the magic happens. The algorithm uses this really clever trick called amplitude amplification. Think of it like a quantum tuning fork. In each step, it pings the system in just the right way to make the correct answer resonate, boosting its probability. And at the same time, all the incorrect answers, they get just a little bit quieter. And you just keep doing that.
Repeat that amplification step over and over, and the result becomes unmistakable. The probability of measuring our target state just skyrockets until it's almost 100%, while all the wrong answers are effectively silenced. And just like that, you found your needle in the haystack.
Now that all sounds amazing, and in a perfect simulation, it is. But what happens when we try to run these beautiful, precise algorithms on a real physical quantum computer? That's when things get, well, a little messy.
So the journey of any quantum program really has 3 steps. First, you write your code in Qiskit. Second, you test its logic in that perfect, noiseless simulator. And then you kind of hold your breath and send it off to run on actual, physical, and very, very noisy quantum hardware.
And that's the absolute key difference between the simulation and reality. One single word: noise. You see, real qubits are unbelievably fragile. The slightest vibration, a tiny fluctuation in temperature, a stray magnetic field, any of it can corrupt their delicate quantum state and introduce errors. Honestly, overcoming this noise is the single biggest challenge in quantum computing today.
And this means the results you get back from a real device look totally different from a perfect simulation. Instead of getting one clean answer 100% of the time, you get a probability distribution. Hopefully, the biggest slice of the pie is the right answer, but you're always going to see this scattering of incorrect results that were caused by all that noise.
There's this quote from a recent study that just nails the state of the field right now. It says, "The ultimate test of any quantum algorithm's efficacy comes from its performance on real quantum hardware." And that's really it, isn't it? It's not enough for an algorithm to work on paper anymore. The true test is whether it's strong enough to give you a useful answer despite the inevitable noise of a real-world quantum processor.
So here we are. We are literally learning to speak a new language, the fundamental language of reality itself. We can now write instructions for the very building blocks of the universe. Now look, the challenges like noise are immense, but the potential rewards, designing new medicines, creating novel materials, maybe even understanding the cosmos, are truly revolutionary. So the only question left is, what are we going to build first?